So we're calculating volumes. Specifically, we're looking at now, it's called the disk method. Okay, so once again, I want to give you guys a fundamental understanding of that, because I don't want you to make it too strict about a formula. It's not really a formula; it's a concept behind the scenes. So think about, you have an area. Let's say an area like this, okay? Some area with boundaries around that, right? That's some areas and boundaries around that. And at the start, for simplicity, let's say some boundaries are sort of like straight edge or something like that, right? Some boundaries are being straight edge, the other part can be bent to whatever fancy thing that is. Right? But generally, we got to start with an area. And so now, let's say on this area right here, let me reconstruct another picture just like that. Right? Got some boundaries. Yeah. So one case, we can set an axis right by one of the straight edge boundary like that, right? And then you know what we're going to do? We're going to take that area and we rotate that around the axis here. So think about, we place a horizontal axis right along the edge. So I'm talking about the axis right along the edge, and then that now becomes what I so call the rotation, right? The rotation axis. You want to say no? Okay. And so rotation axis means now I'm going to take this area, I'm doing this. Right? Rotating. You want to say that? Okay. So start putting in your imagination what's going to happen when we're rotating. There's the axis right here, my pencil strokes right there, right? And if you're rotating it around the axis being the center, right? The center of rotation. So if you place your eyes, so the idea is when you're looking, you're always putting your eyes right by the axis, so your eyes is here. See what I'm saying? When you're looking straight by the axis right here, then in front of you, what you have now is a whole disc. See what I'm saying now? That's why it's called disc method. Okay? So eventually you create something like a bow shape. If it's just nicely bent like that, right? You're creating something like a bow shape. You guys agree? Okay? And then the same way right here, the area, if you place an axis, so in reality, right, you got an area all over. You can place your axis like that and rotate it. See what I'm saying? It becomes something crazy. But we don't want to get into anywhere near that kind of complication yet. So here we're just gonna set it. We're gonna put our rotation axis vertically. See what I'm saying? Okay, and then we're rotating it. Right. So by doing that, well, this is what we get right here. It's rotating like this around the y-axis, okay? Around the vertical axis. So we're gonna get this again, right? Because if we place our eyes, right, we're placing our eyes looking straight into it, right? Each one of these is a disc. Each one of the cross section there is a disc. You guys follow that with them? And so, because we're revolving things like that, right, around an axis, what we have here is now from an area, but rotating it, it becomes a volume, right? See what I'm saying there? It becomes a volume. Guys, I mean, if you're looking at a bottle like this, right? This bottle like that. Forget about this, the spraying part here, right? Just from this part of the bottle down. Think about it. Where does that picture come from? You can think of that as a curve like this. See what I'm saying now? Right? So you got some kind of area here, right? And then with that curve right here now, what's happening when you're rotating it? See what I mean? So you got a model, and your eyes looking straight at it, right? Become a solid that came out from evolving. See what I mean? Okay. And so now how do we calculate a volume on something like this? So the idea now is that any of these, doesn't matter if your rotation axis is the vertical axis or the horizontal axis. You have to understand the idea now is that we think about cutting these into slices, right? Each slice here is a cross section being a disc. That's why it's called the disc method here. You are saying that? And let me clear out the picture and make it even more intuitive. The more I put too much details into that, the more busy it's gonna get. But think about you put a stripe here, right? Put a stripe from the boundary right there of the area perpendicular to the, so the stripe is perpendicular with the rotation axis, right? And then rotating the area around that, the stripe here is gonna create for you a disc. That's the idea of that. You guys with me there? Okay, so a disc, in the way how we put our disc this way, so the disc has to always be perpendicular with the rotation axis. You got me there? Okay. And so in that way right here, each of the discs got a thickness. You got that? Right. No matter how thin it is, but it got a thickness, right? So that thickness there is what? In this case right here, we place a disc to be perpendicular with our rotation axis, and the rotation axis is chosen, right? In this case, chosen to be the x-axis, and thickness makes sense to be a dx, right? Okay, still? The thickness, because the rotation axis is the x-axis, just like that, right? So the disc goes like this. See what I'm saying now? The disc goes like that. So each of the discs, how thin or how thick that is dx, right? Infinitesimally small changes in x. You got that? Okay. So similarly, if you're rotating an area but rotating around the y-axis, once again, each of the cross section is a disc again. Are we good? Right. But then the disc here, what's the thickness? This is thickness. You gotta look at pictures, right? That's the thickness. Sounds good. Now the thickness here, how do I see that? The thickness here is decided as a y. But now we're talking about the idea to get the volume. Now we're getting volume of the whole rotated, the whole revolved solid right here. Then think about we're stacking the disc. Either we're accumulating from start to end, from on the left to the right. Because see, there's a thin disc, being small disc, and then a larger one, right? Depending on where we place our stripe. See what I'm saying? Huh? So the further we go from the start to the end right here, but each disc right here so we got thickness, but it has to multiply. Think about it. The disc like this, right? It got thickness. How do we calculate the volume of a disc like this? Yeah?
Well, it would be the area of a circle using a height of the function as its radius.
That's right. So the area of the circle, right? I don't need to worry about the function whatever, but the area of the circle, which is this bit right here, right? So area of the disc, in this thing right here, right? The area of the disc, and then we multiply with what? The thickness right here. You guys following right there? Right. So I want you guys to focus on that. And so now on any disc, right? We got it's called the cross section, right? Area. Because the disc itself is a cross section, right? It's a cross section right here, or a cross section right there. So it's called a cross section area. Multiplied with the thickness. That's the volume of one disc right here. Are we good with that? Area of the cross section, right? Multiplied with the thickness. That's the volume of one disc. Are we good? Right. So if the discs are perpendicular to the x-axis, then the thickness is dx, right? And the cross section, eventually we're going to express it in terms of as a function of x. So I don't want you to, because that's the way how a lot of textbooks explain it. They try to get it in terms of function, but I want you guys to see this fundamental. And then we're accumulating all of those this volumes, right, from the start to an area here. Well, I'm saying up. So that's the fundamental way. That's how we get the volume, right? The total volume of that revolved solid. Well, I'm saying that cross-section area here, yes, you can also understand it. You can also understand that as the disk area. Okay. More generally, it's a cross section. Okay. So ready to drive it in? All right. So now I'm gonna produce the first problem right here for us to try. So let's call that example 1. Part A. So by part A, first problem here. So after writing it down here, let's look at the problem. And at this point right here, you definitely got to draw the picture, right? There's some nature of these problems that we just can't escape with here. So if you don't like drawing pictures, at least get yourself practice a little bit, okay? But let's sketch the description of the area. The idea is now is that we've got some area, and then we're going to rotate that area around the x-axis right here. You want to say no? Okay. So what's the function of so the area is bounded between this function f of x equals square root of x, right? And the x-axis. So let's go ahead and draw that. The square root function is simply just that. We don't have to get too precise, right? Right? And then so between the x-axis and the curve right there. Okay? So f of x equals square root of x. Very good. Okay. Let me scale it up a little bigger again so I can easily read it. Okay. So from between x equals 0 to x equals 1. So really we have this area. You guys follow it? Okay. And so now we're going to take that area and rotate that around about our x-axis, the x-axis right here. So now we're treating the x-axis as the rotation axis, right? Sounds good. So now in that way right here, then think about we have to produce a stripe. And each stripe right here, when rotated, so each of the stripes has to be perpendicular to the rotation axis. That's the way how we do that around the, and about every, I mean that's the way how we do the disc method here. And so rotating those stripes, we're going to have a disc, right? Follow me on that. Okay? So now each of the discs, let's look at the disc right here. Thickness. What do we have for thickness? Thickness, here, how do we express thickness right here? Yes. The x, right? Just the way how we place our stripes, and the thickness has to be the x. You got to look at the picture, right? And then, see, the area of the cross section is right here, right? Being a circle. Sounds good? So, now we're going to have even a little further right here. How do we find the area of the circle? Cross section area, right? Or how about, let me just even call it more precise right here. This area, how's that? Even though it's generally a cross section, right? But this area is always what? Pi times the radius squared, right? You guys follow it? But how do we determine the radius of any of these discs? Because the radius comes from what? The height of the stripe, right? In the way how the picture looks here. We gotta look at the picture. Sounds good? So the radius is the height of the square. I mean the height of the stripe here. So but the height of the stripe is determined by what? The length from the x-axis out to the curve itself. You guys follow it right there? The length from the x-axis, right, out to the curve itself. So that means in this case right here, it's just going to be our f of x. Okay? And now the radius is all squared, right? Multiplied with pi. Are we good with that so far? Right. And so in this case right here, now what do we have here? The function itself is the square root of x, right? The function itself is square root of x. So now we have square root of x all squared times pi, right? So that's how we generate the disk area over here. And so once again, let's check for consistency. Actually, let's wait for the next step here, and we will be able to check for consistency. But now the disk area and square root of x all squared gives me just x. So really, this area is just pi times x, right? So pi times x times dx. This is the area. I mean, this is the volume of one disk. You guys follow it? And we're accumulating all of those little volumes, right? All of those disk volumes from start being 0. So you start from 0 to end at 1 right here. Now that's going to achieve the whole total volume again. Are you able to follow with me on that right there? All right, so in this way right here, let's check for consistency. You see, our dx was expressed as a differential, our thickness, right, was expressed as a differential dx. And that's why it makes sense. See, I don't want you to go with the textbook version, like get straight into the f of x or whatever, but I want you to understand that mainly we need this area. Okay, and the radius of this area is determined by the distance from the rotation center out to where it hits the boundary. You see what I'm saying now? And then in this case here, since our d thickness is expressed in terms of x, right? So we are pushed down to expressing this as in terms of x. Or we look at that like that. It doesn't always have to be f of x or f of y, right? So don't get stuck with a textbook formula. See what I mean? The point is we got this area being pi r squared. Everybody knows, right? The ancient the Greek and ancient Egyptian came up with that for long ago, right? And now we applied it here. And then so f of x or f of y, whatever, depends on how we see our stripe. See what I'm saying? It depends on how we put our thickness. So our thickness is dx. We need to express that stripe here as a function of x. Does that make sense? Right? And that's why, and then we square that length, right? So now we are ready for the final answer, right? So now accumulating all of this volume right here. Now we're looking at that pi here, the constant coefficient. So it's pi over 2, right? X squared, and we're integrating from, we are substituting it from 0 to 1. Good. So that gives me a, substituting in, right? 0, substituting in gives me a 0. So it's just now all pi over 2. That's the volume of our disc there. See what I mean? Okay. Nice and simple. See, the curve is just the curve that defines the area. It's just a boundary curve here. I don't want you guys to get too hung up with this being a function or not. So this problem, number 1, example 1, problem A is still pretty straightforward. Let's look at another one. All right, so I'm going to write it down right here, part B of the example. It's the area bounded between the same curve and the y-axis. Okay? From y equals 0 to y equals 1. And we are rotating about a y-axis. Right, so now, got the problem written down so far? So once again, let's sketch the area. We actually want, so see, function or not function, that's not important. It's a curve, right? Some kind of curve. And now let's sketch the area right here, the region that we are looking at. So, that's the curve, right? F of x equals square root of x, right? Or you can think of that as y equals square root of x, right? It may be better writing it that way. Good. And then, so that's the curve, but this time is the area between the curve and the y-axis. So it's this area right here. And from 0 to 1. 1 is here, about there, right? That scale again. So it's this area. Same curve, right? But we can draw a completely different region already. See what I'm saying now? And then we're rotating around the y-axis, right? Rotating it around the y-axis, so it goes this way. So now we're going to produce our stripes to be perpendicular. So I keep repeating, the stripe got to be perpendicular to the rotation axis. The rotation axis this time is here. Rotation axis. Okay. And so in that way right here, see each of the stripes gives us there's a thickness for us right here. That's something to note, right? And then when we're rotating it, it's going to become something like this, right? And then you see the picture, the sketch of the picture will give me kind of like something like this, right? See what I mean? Okay. All right. So thickness. What should we call? How should we express the thickness? Dy. See, getting the thickness down will get you successful. Okay. And so now, this area, how do we get the area for each of this here? Famously, pi r squared, right? R is the length of our stripe. Sounds good? Okay. But now, how do I express the length of the stripe? The length of the stripe in the picture, it's limited between the y-axis and this curve here. Sounds good? Okay. But that curve here is written as y equals square root of x. So we need to rewrite. See, the stripe now being placed along the y-axis, right? Perpendicular to the y-axis, to the rotation axis. So we need to re-express this equation here. So we got y squared, right, equals x. You guys follow it? Okay. So it's actually changing from the length here between left side and right side, right? Left side of left boundary and right boundary. And so it gives me really this time pi times the y squared and then square again. Because this is the length of the stripe as the radius, right? Depending on where we put it on the y-axis. Different y value gives us different length area. I mean different length of the stripe. Alright, so you got the disk area and all that. So now let's put it in. So once again, each disk got disk area. This is in the end pi times y to the fourth, right? So pi times y to the fourth, that's this area times the thickness dy. Let's check for consistency. Are they consistent? Yes, our expression here, our differential expression here is in terms of y, right? And then the function we're iterating is in respect to y. So that's why I really refuse to tell my students that this is f of y or g of y all squared. See what I'm saying? That your mind will get stuck into that path, and at some point it's going to make it hard. The point now is that it's just the radius here being determined by from where the rotation axis out to the boundary. Okay. And then if we place a stripe right perpendicular to the y-axis, then yes, you do need to express that height, right, that length here in terms of y. Because to make it consistent with this thickness, right? Good. So good. That over there is the only fundamental I have for everyone. I have that other word. So now that's the area of, the volume of one disk, right? All that here, volume of one disk. So now we're accumulating. We're going to accumulate all of these disk volume from 0 to 1. But think about this. This is from bottom up, right? Bottom up right here. Bottom, right, top. That's how it happens. Okay, so now the final volume here is going to come out pi over 3, right? Oops, wrong one. It's pi over 5 actually. Y to the fifth, right? You go from 0 to 1, right? Just pi over 5. That should be a positive quantity, right? Okay. Any questions for me on this method? Are we good with this so far? Okay. Now, let me call that part, well, how about, let's call it example 2 over here. We want to find the volume, it's all about finding the volume of the solid, right, generated by part A here. So once again, let's sketch the picture, right? So, this region right here is where root 2 is, right? X-axis, the y-axis, that curve. Minus x squared minus y plus 2. Rotate around the x-axis, so the axis of rotation is right here. Okay? And so, with this, once again, once we are given information about the rotation axis, right, which is the x-axis right here, then we have to put the stripe. So it's the rule is that anytime we are given that under this method, right, then the rule is to place the stripe perpendicular with the rotation axis. See what I'm saying? So the way how we place our disk right here, and it's got keep rotating it. So we got a disk right here as a cross surface, right? The thickness is here. Right there, so thickness. help me identify the thickness here. How do I write the thickness? Yeah, right. So now the cross section or the disk area. How do I write the disk area here? Well, famously pi r squared. R here is the length of our stripe here, right? The length of our stripe. So any stripe here has a length being restricted between the boundary between the curve, right? The part of the boundary between the curve, and to hit that rotation axis right here. You guys with me on that still? Oh, great. So in that way, now let's look at that. You see, I purposely come up with this equation right here, right? It was x and y all over, but now we need to express it. This, but I see this curve right here gives the further boundary. You see what I'm saying? Now the upper boundary right here. And so in that way, you have to rewrite it as a y equals minus x squared plus 2. Sounds good? And then once again, it's all due to the fact that the thickness here needs to be expressed in terms of, the thickness expressing it in terms of x. So we need to express this in terms of x, right? So now we have pi times the minus x squared plus 2, right? That's the length of the stripe, right? All squared. Now we are multiplying the thickness with the disk area. The disk area is the pi times minus x squared plus 2. All squared, we multiply with the x thickness. That gives us the one disk volume, right? We're going to be accumulating all this volume. So where does it start and where does it end this time? The region is where that region is. How do we know where the start is and where the end is? So of course, it's the first stripe is placed right here. You guys agree? Right? So it's going from 0, right? So from left to the right, but where's the rightmost endpoint right here? Seems like that point there, right? Let's find out. Minus x squared plus 2 equals 0. We set that equal to 0, right? And then that leaves me x squared equals 2. That leads to x equals plus or minus 2. Which one do we need in this case here? So plus or minus square root 2 is the solution to that equation, but which one of the two solutions do we need here? Just the positive one, right? Positive square root 2. Now positive square root 2 is here. All right, so here we go. So go ahead and take your time. Now for this one, definitely you need to FOIL it out a little bit, right? You can FOIL out the pi right here, 0 to square root 2. Right? FOILing it out, you're going to have an x to the 4th, right? Minus 4 x squared and the 4th. We're going to start doing alphanumeric field calculus. Enough space in here. That equals pi times 1/5 x to the 5th minus 4/3 x cubed plus 4x. Going from 0 to square root of 2. Right? And then you can go ahead and finish with that calculation in the exact expression. We leave that in the exact expression involving root and all that. Right? So go ahead, take your time. You only need to substitute in the square root of 2, right? Because the other part is already a 0 right there. So let's check that this answer applies here. I mean, you guys can do a quick calculation from over here, but how about a pi times 4/5 minus 8/3 plus 4 here, times the square root. We all agree that would be our answer. But technically, I mean, I was a little hesitating to do that overall adding. All right, so we got an answer. Let's switch to another one, shall we? And now I'm going to pick up the pace a little bit. All right, so we found the answer for that one. Part B right here, which should be done quite easily. Same regions, only going to change it around the y-axis. Okay? I didn't really change the region at all, but I'm going to change the rotation axis. As you guys are getting enough experience, I'm going to start picking up fast, a little bit faster. The rotation axis this time is here, right? I want to erase the other portion of the picture. Okay? So now we need to place our stripe horizontal. Horizontally and to be perpendicular with the rotation axis. So the rule is always perpendicular with the rotation axis. Thickness, now how thick that is, right? Now we've got thickness, it's got to be dy. Everybody all good? Okay. And when we're rotating that, we get a surface like that. We got a disk like that, right? So the disk cross section or the disk area comes out by doing this. It's famously pi times r squared. Sounds good? But then the length of the stripe, meaning the radius, this time the length of the stripe is being limited between the y-axis, right? And the outer boundary right here on the right-hand side. See what I'm saying? So we got to figure out, because we see at different y value, we got a different horizontal disk, right? Okay? And so in that way right here, it makes sense that we have to express that in terms of y right here. So the same curve right here. I'm going to go about 2 minus y equals x squared. Are we good with that? Right. And then that, I'm going to take the square root right here. Right? X equals, we've got plus and minus square root of 2 minus y. Are we taking the positive or the negative of the square root? Positive, right? Yes. So we take just the positive. Last one here, x expressed as a function of y, square root of 2 minus y. Okay. So now we have pi times the square root of 2 minus y, right, all squared. That's how we express our disk area like that. And let's check for consistency. Consistency right here. See, when we multiply these together, the disk area being pi times the square root of 2 minus y, all squared. When we multiply that with the dy, it's all consistent, right? The differential expression here is in terms of y, our thickness, our function of the area, right, completely in terms of y. Sounds good? All right. And so in that way, right here, we're ready to advance. That's the volume of one disk, right? We're accumulating it all from the bottom up, right? Those disks are stacking from the bottom up here. 0. What's the highest point up here? From this equation, you guys can tell. We can also think of that as y equals minus x plus 2 again, right? This is the highest point has to be 2 again. The parabola, it's that nice parabolic shape or that nice parabola where it peaks out at 2. Right? So 2 going up there. So that's going to get us our volume. See what I mean? Alright, so the square cancel with the square root and the pi can be placed in front. So we're looking at pi times the 0. Integral from 0 to 2. Okay, and then we've got 2 minus y. And then dy here. Look good? Alright, so the with this work here is, and don't expect it's the same answer with the earlier problems, right? It's completely different solids here. So it's pi times we've got 2y minus 1/2 y squared, and we evaluated this from 0 to 2. So we've got a pi, right? Here we've got a 2 times 4, 2 times 2, making it a 4 minus that's here, that's a 4 divided by 2 times 2. The final answer here comes out being a 2 pi, right? That's how it happens. Right. Okay, let's bring in another problem where you can see the power of calculus here, actually. Let me use the other board so I don't have to waste time writing erasing it. Okay, so example 3 right here. Let's finish writing it down. Let's draw the picture. Okay, it's just a cone. It's just a cone, but we want to see how we can apply calculus in here. So don't use the high school geometry formulas or anything like that. Okay, but the cone looks like this, according to the description. Right? It's got base circle with radius 3. You guys following? Right. So that's 3. Right? And then the height right here being 6. Are we good? Okay, so that's the drawing of the cone. So now in that way, think about it, the volume of this cone, there are a lot of varieties that you can go. Because no one told you any specific rules, so you can go like this. Draw a line from, this is 6 right here, this is 3 right here. 3 right here. You have a region like that. See what I'm saying now? And then this region here, you can just simply, right from the picture, you can just simply rotate that around the y-axis. See what I mean? Okay. And then you're going to get the cone. And so now, once you identify your goal, see, here you even decide the rotation axis yourself, right? Okay. So now, let's do the calculation. If you now know that this cone came out from rotating that area, right, restricted by this slanted line right here, right, around the y-axis, then how do we place our disc right here? Like that, right? Our stripe has to be perpendicular with rotation axis. So we now got thickness being y. You guys with me? Okay. Easy enough with that, right? And then the cross and the disc area, right? This area is simply how long that stripe is. So you just need to figure out the equation for this line right here. You guys follow it? The line is easy enough, right? But remember, this equation has to be in terms of y. Right? Because this area is always a pi times the r squared. And by the way, see, for an equation like this, I mean, if it comes more natural for you to express it in terms of x, that's okay. What slope is this? Over 3, right? Down 6. See what I'm saying now? So it's a slope negative, -2 right there, right? It's down 6, and so -6 over 3 right there. Looking at -2, right? Plus 6. That's the way how we're writing it more naturally. But then we're gonna need to express that in terms of y. See what I'm saying now? So the same equation here, I'm gonna subtract the 6 over, right? So I have y minus 6, right, equals -2x, and I'm even gonna divide both sides by -2, so making it, that will lead to x, right, equals minus 1/2 y, right, plus 3, you got that? Right, so now I'm looking at this area being a pi times minus 1/2 y plus 3 all squared. So now the volume of one disc is going to be pi times -1/2 y plus 3 all squared times the thickness dy. Things are all consistent in terms of the variables, right? And we're accumulating from the bottom up. Bottom is 0 here, either way how we place our picture. Are we good? And then up right here, up point right here is 6, right? We're completing out that volume, that interval, we get the total volume. See what I mean? Right? And that's the part where we're going to need to do a little bit of algebra over here. We can pull out the pi over here from 0 to 6, right? And then here we're looking at the positive 1/4 y squared minus, and then 2 times 2 is 3y, right? Plus 9 there. Check my foiling work for me if you could. Should be correct. Alright, now that's gonna make it pi, right? Times, now in parentheses, y cubed over 1/12 times y cubed, right? Minus 3/2 times y squared plus 9y there. We're substituting it to 0 and 6. And that actually, for you to double check that, right? Finish out a final calculation. Right. So any questions from you? And then once you've had that final answer, you should be also able to compare the answer we found here using the calculus with the answer we found from the high school formula, right? And it should agree. The two methods should agree right here, but the aim here is to use calculus for that. See what I mean?